Today we are going to learn theorems on limit superior and limit inferior. Theorem number 9. Theorem 9. Let Sn is equal to 1 to infinity be bounded sequence of real number. Let sequence Sn n is equal to 1 to infinity be bounded sequence of real number. Be bounded sequence of real numbers. Number 1, if limit n tends to infinity of superior of Sn is equal to capital M, then for any epsilon positive, result is Sn is less than capital M plus epsilon. Sn is less than capital M plus epsilon for all but a finite number of values of n. For all but a finite number of values of n, values of small n. B, Sn is greater than capital M minus epsilon. Capital M minus epsilon for infinitely many values of n. For infinitely many values of small n. Number 2, if limit n tends to infinity of inferior of Sn is equal to small m, then for any epsilon positive result C, Sn is greater than small m minus epsilon for all but a finite number of values of n. For all but a finite number of values of n. D, Sn is less than m plus epsilon for infinitely many values of n. For infinitely many values of small n. This is the statement of theorem number 9. Theorem number 9. We prove this theorem by method of contradiction. Proof. We prove this theorem by method of contradiction. Suppose A is not true. If possible, we suppose A is not true. That is, A is false statement. Suppose small a is not true. That is A is false. False statement. Therefore, Sn is greater than or equal to m plus epsilon for infinitely many values of n. Here, Sn is less than capital M plus epsilon for all but finite number of values of n. Therefore, we write this statement as Sn is greater than or equal to capital M plus epsilon for infinitely many values of n. For infinitely many values of n. Values of small n. Sn is greater than capital M plus epsilon for infinitely many values of n. Therefore, for any n belongs to I, the set Sn plus 1, Sn plus 2 and so on contains number greater than or equal to m plus epsilon. For any n belongs to I, for any small n belongs to I, that is any positive integer, the set Sn plus 1, Sn plus 2 and so on contains a number greater than or equal to m plus epsilon. Greater than or equal to capital M plus epsilon. Therefore, we write list upper bound of the set Sn plus 1, Sn plus 2 and so on is greater than M plus epsilon for all small n greater than or equal to capital M. Therefore, we write list upper bound LUV of the set Sn plus 1, Sn plus 2 and so on greater than or equal to capital M plus epsilon for all n belongs to R. For all n belongs to I. But Mn, capital Mn is list upper bound of the set Sn plus 1, Sn plus 2 and so on. But we know capital Mn is equal to LUV of the set Sn plus 1, Sn plus 2 and so on. Therefore, capital Mn is greater than or equal to capital M plus epsilon. Capital M suffix n is greater than or equal to capital M plus epsilon for all n belongs to R. For all n belongs to R. Since by hypothesis Sn is bounded sequence of real numbers, therefore sequence Mn converges. Since by hypothesis Sn n is equal to 1 to infinity is bounded sequence of real numbers. First we take limit of this result as n tends to infinity and we write limit n tends to infinity of LHS is greater than or equal to limit n tends to infinity of RHS. Limit n tends to infinity of capital Mn, taking limit on both the sides as n tends to infinity. Taking limit on both sides as n tends to infinity. First we write limit n tends to infinity of small n is greater than or equal to capital M plus epsilon. Or limit of RHS. Limit of RHS, that is limit n tends to infinity of capital M plus epsilon. Capital M plus epsilon, which is equal to limit n which is equal to, there is no n, therefore limit of m plus epsilon is again capital M plus epsilon. That is limit n tends to infinity of capital M is greater than or equal to capital M plus epsilon. Epsilon is positive real number that is given in hypothesis. So we can add here for any epsilon positive greater than 0. Epsilon is positive real number greater than 0. Since my hypothesis sequence Sn n is equal to 1 to infinity is bounded sequence. Therefore, sequence Mn converges. Therefore, sequence capital Mn n is equal to 1 to infinity converges. Sequence capital Mn converges, and limit n tends to infinity of superior of Sn is equal to limit n tends to infinity of capital Mn. Therefore, we write limit superior of Sn, limit n tends to infinity of superior of Sn is greater than or equal to capital M plus epsilon. Since epsilon is positive number, therefore M plus epsilon is strictly greater than M. Since epsilon is positive number. That is, limit n tends to infinity of superior of Sn is strictly greater than M. Strictly greater than M. This is contradiction to our hypothesis. This is contradiction. This is contradiction to our hypothesis. Limit n tends to infinity of superior of Sn is equal to capital M.
Now we prove the B. 1B. Proof of 1B. Proof of B. We prove the second B by method of contradiction. Suppose, if possible, we suppose this B is not true. Suppose B is not true. That is B is false statement. Therefore, for some epsilon positive, Sn is greater than S suffix n is greater than capital M minus epsilon for finite number of values of n. Sn is greater than M minus epsilon for finite number of values of n. Finite number of values of n. Here, Sn is greater than capital M minus epsilon for infinitely many values of n. We have replaced infinitely many values of n for finite number of values of n. But there exists capital N belongs to I, but there exists positive integer capital N belongs to I, such that Sn is less than or equal to capital M minus epsilon for all small n greater than or equal to capital N. Sn is less than capital M plus M minus epsilon for all small n greater than or equal to capital N. Therefore, we know theorem, if Sn and Tn are bounded sequences of real number and Sn and Tn both are bounded sequences of real number and Sn is less than or equal to Tn, then limit superior of Sn is less than or equal to limit superior of Tn. And limit inferior of Sn is also less than or equal to limit inferior of Tn. By using theorem, limit n tends to infinity of superior of Sn. Therefore, by using theorem, limit n tends to infinity of superior of Sn is less than or equal to limit n tends to infinity of superior of capital M minus epsilon. Limit superior of Sn, limit n tends to infinity of superior of Sn is less equals capital M minus epsilon. Capital M minus epsilon. Epsilon is positive. Since epsilon is greater than 0, therefore M minus epsilon is less than, therefore capital M minus epsilon is strictly less than capital M. Therefore we write limit n tends to infinity of superior of Sn is less than or equal to capital M minus epsilon, which is strictly less than small m. Limit n tends to infinity of superior of Sn is strictly less than capital M. This is contradiction to our hypothesis 1. This is contradiction to hypothesis 1, that is limit n tends to infinity of Sn, limit n tends to infinity of superior of Sn is equal to capital M. Hence B must be true. Hence B is true. Hence the proof of B. Hence the proof of B. Proof of 2C. We prove C by method of contradiction. If possible, we suppose that this C is not true. Suppose C is not true. That is, C is false. That is, C is false statement. C is false statement. Then for some epsilon positive, Sn is greater than m minus epsilon for infinitely many values of n. Sn is less than small m minus epsilon, less than or equal to small n minus epsilon for infinitely many values of n. Sn is less than m minus epsilon for infinitely many values of n, values of small n. Then for any n belongs to I, for any n, small n belongs to I, the set Sn plus 1, Sn plus 2, S suffix n plus 2 and so on contains a number less than or equal to small m minus epsilon. Therefore, GLB, greatest lower bound, GLB of the set Sn plus 1, Sn plus 2 and so on less than or equal to small m minus epsilon for all small n belongs to I. For small n belongs to I. But we know small mn is equal to GLB of the set Sn plus 1, Sn plus 2 and so on. Therefore, we write small mn is less equals small m minus epsilon. Small m minus epsilon for all n belongs to I. For every positive integer n belongs to I. Taking limit on both the sides as n tends to infinity. Taking limit on both sides as n tends to infinity. Limit n tends to infinity of small m less equals limit n tends to infinity of small m minus epsilon, which is equal to small m minus epsilon. Since Sn is bounded sequence of real number and therefore small mn converges and limits inferior of Sn is equal to limit of mn. Since sequence Sn n is equal to 1 to infinity is bounded sequence of real number, bounded sequence of real numbers, bounded sequence of real numbers. Therefore, sequence small mn n is equal to 1 to infinity converges and limit n tends to infinity of inferior of Sn. Inferior of Sn is equal to limit n tends to infinity of small mn. Therefore, we write limit n tends to infinity of inferior of Sn is less equal small m minus epsilon. and which is strictly less than small m since epsilon is positive number. That is, limit n tends to infinity of inferior of Sn is less than small m. This is contradiction. This is contradiction to hypothesis 2. That is, limit n tends to infinity of inferior of Sn. Inferior of Sn is equal to small m. Therefore, C is true. Therefore, or you may write hence C is true. C is true. Hence the proof of C. Hence the proof of C. Proof of 2D. We prove D by method of contradiction. Suppose D is not true. That is, D is false. False statement. Sn is less than small sn is for some epsilon positive, then for some epsilon positive, some epsilon positive, Sn is less than, S suffix n is less than small m plus epsilon for infinitely many values of n, for a finite number of values of n, for finite number of values of n, values of small n. Therefore, we have changed this infinitely many values of n by finite number of values of n. Sn is less than small m plus epsilon for finite number of values of n. But for any n belongs to I, but for any small n, or but there exists capital N belongs to I. Capital N belongs to I. There exists positive integer capital N belongs to I, such that Sn is greater than or equal to small m plus epsilon for all small n greater than or equal to capital N. Means for infinitely many values of n, Sn is greater than or equal to small m plus epsilon for all small n greater than or equal to small n greater than or equal to capital N. Therefore, by using theorem on limit superior, limit superior and inferior, limit inferior of a sequence, limit superior and limit inferior, limit inferior of a sequence, that is, Sn is less than or equal to Tn for all n belongs to I. Sn and Tn are bounded sequences of real number. Sn and Tn are bounded sequences of real number, and Sn and Tn Sn is less than or equal to Tn for all n belongs to I, then limit inferior of Sn is less than or equal to limit inferior of Tn. Limit superior of Sn is also less than or equal to limit superior of Tn. Therefore, we write limit inferior of Sn. Limit n tends to infinity of inferior of Sn is greater than or equal to limit n tends to infinity of inferior of small m minus epsilon, which is equal to m minus epsilon. Therefore, limit n tends to infinity of inferior of Sn is greater than or equal to m minus epsilon. Since epsilon is positive, since epsilon is greater than 0, therefore m minus epsilon is less than here is m minus epsilon is less than m. Here is Sn is greater than or equal to m plus epsilon. Therefore here must be m plus epsilon. This is m plus epsilon. M plus epsilon is positive. Therefore, m plus epsilon is greater than m. Therefore, we write limit n tends to infinity of inferior of Sn is strictly greater than or equal to m plus epsilon, which is greater than m. Limit n tends to infinity of inferior of Sn is greater than m, small m. This is contradiction. This is contradiction to hypothesis 2, that is limit n tends to infinity of inferior of Sn is equal to small m. Here Sn is greater than or equal to small m plus epsilon. Therefore, by using theorem on limit inferior, if Sn and Tn are bounded sequences of real number and Sn less than or equal to Tn, then limit inferior of Sn is less than or equal to limit inferior of Tn. Limit inferior of Sn is greater than or equal to limit inferior of m plus epsilon, RHS, m plus epsilon, which is equal to m plus epsilon. Therefore, limit n tends to infinity of inferior of Sn is greater than or equal to m plus epsilon. Since epsilon is positive, therefore m plus epsilon is greater than m, strictly greater than m. Using this result here, we obtain limit n tends to infinity of inferior of Sn is greater than or equal to m plus epsilon, which is greater than m. Limit n tends to infinity of inferior of Sn is equal to small m. This is contradiction to our hypothesis. Limit inferior of Sn is equal to small m. Therefore, D is true. Hence, we write, hence, D is true. D is true. Hence, the proof of theorem number 9. Thank you.